Hello everybody, this is lecture 3 of the measurement and instrument course. Today I will speak about the errors during the measurement processing. So there is two types of errors, systematic error and random error. Systematic error means that in the output reading there is some error in one side of the correct reading, either the positive or negative. This comes because of the system disturbance during the measurement or the effect of the environment change. So either the system disturbance or the environment, okay? Other sources may be the drift in the instrument characteristics, poor calibration, uncalibrated instruments. So it's related mainly to the device that you use to measure and the environment. The random error, it's a perturbation of the measurement. Maybe in either true or both of the sides of the true value, and it's unpredicted effects. So you can't make some major change for it. So it's almost accurate or almost equal for a series of measurements. So if you measure the same quantity again and again and again, you find that the random error repeats itself. Such a perturbation can maybe small, but sometimes occur from time to time to be large perturbations, okay? So it can be it happen because of the measurement that taken by human observation. For example, he see the analog meter, and if there is interpolation between 2 points, for example 4 and 5, and he want to read the point between 4 and 5, 4.5, 4.6, so there is an error in the measurement, okay? Also the electrical noise may be affecting that, okay? Now for the systematic error, again it happened due to the measurement or the environment input, a problem in the instrument component, a connection between point and point, there is some error arise. So for example, let's see this electric circuit, and we want to measure the resistance here. For example, here we have to read all this resistance in this circuit. For example, here R2 and R1 is series, however they are parallel with R3, so this is R parallel between C and D, RCD. Then they are then you can take the RCD, this is equivalent of this equation. Then RCD is in series with R4 and parallel with R5, because we take about R5, so they are parallel with R5. Then you can easily find RAP. Then I can just replace RCD with its equivalent value to get this value. Then this is the RAB, okay, the equivalent value of the all resistance in this circuit, and there is a source of the voltage, and there is a current. The current is the source over the equivalent resistance, plus there is a small resistance inside the device that we use to measure, okay? So the EM over E0, EM is the voltage over RM, which is RM multiplied by E0 over the summation of the other two. EM over E0, it's this value, you just remove E0. So here, if I have a value for this resistance, I can get the equivalent resistance, okay? I can get this one, and I can find EM over E0. If I want to get the error here for this circuit, electrical circuit, E0 minus EM, so it is 1 minus this value. And if he giving us the RM, this one, the internal resistors, okay? So it's here we have 0.95 E0, it's equal to this value. So there is some error, small error, 5% of the value. Now, error due to environment inputs. Environment inputs may be, for example, assuming that a box weighing 0.1 kilogram, which when it is empty. If we put the box into the bathroom and observing a reading of 1 kilo, this is not immediately giving us the exact reading. This is maybe for a true of 0.9 inside the box, an empty box with 0.9 bias on the scales due to the temperature change, or 0.4 of the true and 0.5 of the bias. Okay, so real value plus the environment value. Okay, so the magnitude of any environment input must be measured before we measure the real quantity, so we can take it into account. Okay, now the wear or the systematic error in the instrument components, that it's frequently developed over a period of time, so it's not occurring directly. So the recalibration normally solve this problem. Okay, the connecting leads, maybe I connect some wiring to the circuit that I want to measure, but this wiring already have a resistance. For example, here he giving you an example of a resistant thermometer. So if I have a wire of 100 meters, then this have a resistance of such length 20 gauge copper wire, so it is 7 ohm, and therefore it's affected by the temperature 1 milli ohm per Celsius. So if I have R equals 7 at temperature 20, then with TC 1 milli ohm over Celsius, so I have R0 plus a changeable value according to the temperature in the room that I make the measurements. Okay, now the reduction. I know now what is the systematic error, what is the details that's or the different causes for these errors. Now how I can reduce it, this 6 ways of reduction. The first one, careful instrument design. I designed the instrument carefully because so I reduce the sensitivity of the instrument due to the environment inputs, okay, as low as possible. So it should be designed from a material with a resistance have a very low resistance temperature coefficient. However, this is make a trade-off between high cost of redesign. If you design an instrument with such material, it will be a high cost, and the alternative of accepting the reduced measurement accuracy. So there is a trade-off between the high cost and the accepting of the reduced measure accuracy. Okay, another method is the method of opposing the inputs. So I measure the environment input, I make some opposite measurements. So it's like you subtract the environment inputs using something that reduce it. For example, here, and this is a millivoltmeter. Here I measure something in the coil. It's change its value according to the temperature. So we put here a resistance which is change its value according to the temperature, but in the opposite direction. So whenever the coil changes the resistance, if the resistance of the coil is changed, the R coil or the resistance R component in the circuit, it change it's the temperature coefficient. It's equal in magnitude So it's equal to the coil resistance that's sensitive to the temperature, but in the opposite, so they cancel each other. Okay, approximately the same, they cancel each other, and the total resistance that we measure already approximately the same, because we use something that cancel the environment input. Okay, now the high gain feedback, another way of reducing the systematic error. If we measure the voltage, we make the coil to change over the displacement inside the analog device, then we have some change environment effects, dA, dC, ds. So all of them we can make that like this: E0 equal to Kf x0. So it should be like equivalent to all of them, and I measure the value, I enter to the feedback device, and the feedback device introduce the E0, so I subtract EI minus E0. So the value here, it is EI, it's almost the value that I want. Okay, it's something in the idea it's like the opposite value, but here we use a feedback device. Okay, now the calibration, which we mentioned before in the previous lecture. Calibration, it's a very important act for any instrumentation, so we should follow the procedures introduced in the data sheet that come with the instrument. The instrument usually come with a paper that giving us some instruction, guiding for how to calibrate the device. Okay, so it's normally get rid of the errors due to the instruments by making calibration regularly. Okay, manual correction of the output reading, so this is done by the human being that making the measurements. If the human being, the technician, can reduce the error by calculating the systematic error and make the appropriate correction to the readings. Okay, which this is not an easy task, which it's done by the experienced technician, and today it's done automatically by the intelligent instruments. So another way, intelligent instrument has extra sensors that measure the value of environmental inputs and cancel it directly. So it is very effective because it can deal with the systematic error, and errors can be attenuated. So the final output will be plus some error, but very low level in many cases. Okay, now the other we now speak about the systematic error. Now the random error, as I stated before, it's error that's unpredictable variation in the measurement system, and it's equal for a series of measurements. Then we can have some expectation about it. So for example, assuming that we have measurements like this, x1, x2, x3 for the same value, or for the same for the same value that you want to measure, you can take the average, or you can take the median meaning the value in the middle of all these measurements of the data set. So example, we have all of these measurements. We can see that x mean it's equal to 409, x median is 408. So the value, it's different. What is meaning by that? For example, this is we measure both of them to see if the median value tend toward the x mean. That's meaning that after a number of measurement increases. Okay, because of the measurement very small here in set A and set B, this is different. There is a huge difference when the measurements increase as increase in number, the median tend toward or be the same as the x mean. Okay, the variance and standard deviation, I know that you take this before, but we use it here. So you measure the deviation error, you measure the value minus the x mean, this is the deviation. The variance, you take the deviation square of summation over all of them over the number, this is the variance. And the standard deviation, the square root of the variance. Okay, now you can calculate for set A, set B, set C all of these value, x mean, v, and sigma, to find that these values compared from each set of the that we have of measurements, that when the v and sigma tend to be reduced, there is a maximum and minimum, of course. They range between the maximum and minimum. When they decrease, that's meaning that the average process has reduced the random error close to zero, and we have a confidence that the mean value is the number, is the value or the exact value of measurement. Okay, that you understand. When here it's 11, here it is 2, here it is 1.8. so as the number of measurements increase, the value of the deviation and the variance decrease, and we have confidence that this value, the x mean, is the exact value. We have now reduced the random error. Okay, and this is very close to the exact number, exact value of the that we want to measure. Okay, that's it for today. Thank you for listening.